One tool that we can use when we are investigating the solution to a differential equation is called a slope field. So to give you the idea, imagine this differential equation, f prime of x equals 2x. Can you solve this in your head? So you need an antiderivative of 2x, and I hope you think of x squared. The thing is, we don't know if the solution is f of x equals x squared, or f of x equals x squared plus 7, or f of x equals x squared plus 1. So the best we're going to be able to do, I'll write it down just so it's written down somewhere, is say that f of x is going to equal x squared plus some constant. And imagine what that looks like. It looks like a parabola, but we don't know if it's a parabola with its vertex at the origin, or scooched up one space, or scooched down 4 spaces. But we know it's going to look like a parabola, and we know that the y-axis is going to be the axis of symmetry. So a slope field is a way of approximating a graph of the solution without even actually having to solve the differential equation. So this is something you will be expected to do on the AP test. You'll be expected to produce a slope field diagram of your own. You'll be expected also to inspect a slope field diagram and draw conclusions from it. So we're going to practice both. So here we're going to make our very first slope field diagram. So I've given us probably too many dots, but we'll be all right. If we get really sick of it, we won't fill in all of the dots. So I'm going to make a t-chart. What I want to do is investigate at any point x comma y that happens to be in my picture. I want to figure out what the slope is going to be. So here's my plan. And I'm going to draw in a teeny tiny piece of the graph. Since I know the slope, I know how steep my graph is supposed to be at that spot. So just for example, here is probably your favorite ordered pair, 0, 0. Now I'm just going to look at this differential equation. I already know the solution. I wrote it up here. But we're just going to, what if we didn't know the solution? Could we still draw a picture of what the solution graph must look like? So when x equals 0 and y equals 0, my slope, dy dx is another name for derivative, it's another name for slope, is going to equal 2 times x, and here I've said x is 0. So 2 times 0 is 0. That tells me that the place on this graph where x equals 0 and y equals 0, my graph should be flat. It should have a slope of 0. So what I do is I draw in a teeny tiny line segment with slope 0. And obviously that means horizontal. Slope 0 means horizontal. Now I can keep going. In fact, I'm going to keep going. You'll get the hang of it, so it doesn't always feel like you have to keep going. But here, as I will let x equal 0 and y equal 1, my slope is still going to be 2 times the x-coordinate, 2 times 0. 2 times 0 is 0. So at the place on my graph where x is 0 and y is 1, which I think is here, I'm going to have, again, a teeny tiny piece of a graph that's horizontal. So a teeny tiny line segment with slope 0. And it turns out I could keep going because I kind of picked this easy one to start with. It doesn't matter what my y-coordinate is. If my x-coordinate is 0, it turns out my slope seems to only depend on x in this case. So I'm going to have a slope of 2 times 0, which is 0. So I'm going to draw teeny tiny horizontal line segments at any place where I have an x-coordinate of 0. These are all going to be 0, 0, 0. And I'm going to continue this graph. Look what happens when I let x equal 1. When x is 1 and y is 0, my slope is going to be, here's my slope function, 2 times the x-coordinate. So 2 times 1 is 2. So I'm going to come to the place on the graph where x is 1 and y is 0. And I'm going to draw a teeny tiny line segment with slope 2. Now I don't need you to get out a ruler and, measure up to and over 1 or anything like that. But I do need you to know that a slope of 2, it's uphill, right? positive slope. It's going to be steeper than any slope of 1 you might decide to draw, although we won't have any in this picture. It's going to be less steep than a slope of 4. So here's what I do. When x is 1, I say my slope is going to be 2. And it turns out, I'm going to have this same pattern I had with my zeros. No matter what the y is, notice the only variable in my slope function happens to be x. So I could keep making this table, and I would notice that anytime my x was 1, it wouldn't matter what my y is, my slope would be 2. And I'd have these teeny tiny, oops, that guy should be like his friends. In theory, these guys are all parallel. They're steeper than 45 degrees. Nobody's going to get out a ruler and measure your angles either, but all of your slope pieces should be correct relative to each other. If I went on to try negative x values, anytime I had a slope of -1, I would have, when I had an x value of -1, I would have a slope of -2. So these should be about the same steepness as the ones I just drew, but these ones are going downhill since the slope is negative. This is much easier to do with your pencil. You'll have more luck than I'm having on my iPad here. So what about if you could keep your table going. I guess I haven't been keeping up with my table. I need to know what the x and the y is and what the slope is going to be. What if I let my x equal 2? Pick any y you want. 2 times 2 times 2 makes 4. And it's going to turn out that no matter what my x is, no matter what my y is, when my x is 2, my slope is going to be 4. So this I should make even steeper. You're not going to have a lot of luck making this picture even further out to the left or the right, because it's going to be really hard to draw something steeper than 4 just with your pencil. But computers are really good at making these drawings. Oops. It's not that those necessarily need to be longer, but they definitely need to be steeper than the other ones. These are going to be slope -4. Okay, so a couple things. On an AP test, the greatest number of dots of places where you've been asked to put in a slope field piece is, I think, 9. So don't think that you're going to have to make a picture this big on the AP test. And number 2, check this out. We said that the solution was supposed to be f of x equals x squared plus c. So a parabola with its center, with its axis of symmetry at the y-axis, but maybe like shifted up or down, we're not really sure. We don't have enough information. So, but when you look at the slope field diagram that you've drawn, don't you get the feeling that you have a picture of a bunch of parabolas that are getting shifted up and down the x-axis? Up and down the y-axis is what I meant. So that's the idea of a slope field diagram. Without ever I didn't refer to this solution anytime I was making these little slope pieces. But at the end, I end up with a picture that gives me sort of an idea what the shape of my solution is going to be. Here's your first slope field diagram. We're going to do the next example on your handout here. Just notice that I took this example from your textbook. It's a great problem to do. When I made the little dot diagram, I put in way too many dots. It's not going to be any fun to try to make a slope field diagram with all of those dots. So I've crossed out a bunch of them. This is going to match the picture on page 328 in your book if you're more comfortable looking there. We're going to make a slope field diagram for this differential equation, and here's what it's going to look like. So I need 3 columns. I'm going to use x, y, and I'm going to figure out the m that goes with them. So a couple ways to start. Some people like to start at 0, 0, and calculations are usually pretty easy. I'm going to try to start from left to right, I think. So I'm going to use an x of -1, because notice, of all the dots I haven't crossed out, the furthest left is x equals -1. Then I'll start with my y, I'll use the lowest down one and I'll move up. So this point here is -1, -1. And I'm going to compute my slope. That's going to be 2 times -1 minus -1. That's me replacing the x and the y in my derivative function with the x and... I chose -1. I said I was going to use x equals -1 and y equals -1. Okay, so this is 2 times -1 is my x minus -1 is my y. That makes -2 plus 1, which is -1. Take as much room and as much time as you need to perform these calculations. I like to collect all my work in this sort of, I guess you can't call it a T-chart. It's got 3 columns in it. So that tells me that at the place where x is -1 and y is -1, I'm going to have a slope of -1. So what does a slope of -1 look like? It goes downhill at a 45-degree angle. Nobody's going to get their protractor out when they're grading your AP test to make sure that's a 45-degree angle, but we're going to want to make sure that all the rest of the slope pieces that we draw in are correct relative to this. And if it didn't go downhill, it'd for sure be wrong. So I'm going to keep my x's the same, and I'm going to let my y's go sort of up that left column. Here, if y were 0, I'm going to do this calculation over and over. That's going to be 2 times -1 is -2 minus 0, which would be -2, which is downhill and steeper. In theory, all your slope pieces should be approximately the same length. What we're looking for is that you change their angle according to the correct slope. If I let x equal -1 and y equal +1, it's going to be 2 times -1 minus +1. Ooh, -3. Getting steeper. This is hard to do. I'm not going to lie to you. To draw a slope of -3 and the next one's going to be -4. Nobody would laugh at you if by the time you got to your steepest slope, it looked almost vertical. That would be pretty normal. Which is why we let computers do this most of the time. And if I let y equal +2, this is going to be -2 minus 2 makes -4. So even steeper. All right. I'm going to make myself some room here. I'm going to try the next column of x's. Those are going to be the places where x equals 0. So here we go. When x is 0 and y is -1, I'm going to have a slope of 2 times 0 minus -1, which makes +1. So this is going to be uphill at a 45-degree angle. 0 and 0, that's going to be a slope of 0. 0 and +1, that's going to be 2 times 1 minus 1. Nope. 2 times 0 minus 1. 2x minus y. That's a slope of -1. That's 45 degrees downhill. Yours should probably be a little bit straighter, the ones I'm drawing. It's a little tricky to do with the iPad, but thank you for your patience and your flexibility. So if I had one more that I've got here, 0, and y could have been 2. It's going to be 2 times 0 minus 2, which is a slope of -2. And so it's not quite as steep as the slope of -4 that's right next door to him. You could continue your table. I don't know, maybe the fastest for me might be to come over here to make this section, x and y and m. Now I'm going to let my x's equal +1. My y's are going to go from -1 to 2. And I'm going to calculate. So 2 times 1 minus -1. That's 2 plus 1 is 3. Ooh. There's a slope of +3, even steeper. All right, here I'm going to have 2 times 1 minus 0 is 2. 2 times 1 minus 1 is 1. 2 times 1 is 2 minus 2 is 0. So I'm going to have slopes of 3 and 2 and 1 and 0. So the order in which you fill in those points with their teeny tiny line segment does not make a difference. Your goal is to just get a tiny line segment with relative slope relative to all the other points that you're marking by the time you're done with your slope diagram.